section 10.6 when we're looking at pulleys, and this seems to be the place where the problems really come in for the mechanics in year 12. I'm recording this in 2019, so since this new syllabus has come in, I've actually taught this topic twice. Last year, the class that I taught it to, this was definitely the hardest thing that we did on the mechanics, full stop. The current year, they haven't had a chance to really get their teeth into this yet. In fact, it was just today that I did this example with them. So for me, this is the second time I've done these examples within 24 hours. So let's see how it goes. If you're jumping in just to look at this video just on the pulleys, I'd recommend that you go back a couple of videos in the playlist and look at the introduction to the connected particles section, because there's a lot of advice there about how to deal with connected particles and so on, and I'll be slightly sort of referring to that. Of course, do what you want, start here if it makes sense, if it helps, great. But there's some things about the way I'd suggest you approach these questions in general, which you might want to see the first half of that video. Okay, so there are two sorts of situations with pulleys. Situation number one is we've got a pulley here, probably fixed to a ceiling or something like that, and we've got a mass on this side and a mass on this side. We'll always have a light inextensible string because we want the tension to be the same all the way through. If the string's not light, then this bit at the bottom this bit at the bottom has some mass. So this bit at the top up here is supporting the mass of this bit down here at the bottom. So the tension would be different all the way up the string. And if it's stretching, if you think about a rubber band stretching, the tension is not the same all the way. In fact, I've got one here. Let's have a look. If I stretch the rubber band, I'm stretching it, but I've got a different tension here to here. It's perhaps a bit of a bad example because I might have the same tension all in the bit that I've actually stretched. But the idea is, if you've got a stretchy thing, the tension doesn't have to be the same all the way along it. So light and extensible string, it's not going to stretch. It's going to have the tension the same all the way through it. The tension is marked on like this. It's stopping this object falling down, so it's pulling up on this object. It's stopping this object falling down, so it's pulling up on this object. If you're the pulley, then cover up these bits. It's pulling down here and pulling down here because because that's what it's doing. The pulley, it's pulling down on the pulley. So strictly speaking, the pulley has a reaction force from the ceiling that stops the pulley accelerating downwards. But we don't normally worry about that bit because that's sort of too far away from our system. Really, this is the bit of the system we're going to deal with. This object is going to have a mass pulling down here, and this object is going to have, a weight pulling down here because it has a mass. This object is going to have a mass and it's going to have a weight pulling down here. So those are the forces involved. And in almost every single question, those are all the forces that we have, okay? Now, ask yourself this question. First of all, this pulley is going to be smooth, okay? If this pulley isn't smooth, then there will be friction forces here. This pulley is also going to be light, and the reason it's going to be light is because if it's not light, then that means that we have to consider the turning forces as the pulley turns around. So imagine having a great big heavy weight stuck on here on the pulley, right? If it wasn't light, we can have a mass stuck here, and imagine that as it turned around, it would be very different when that was at the bottom to when that was at the top and about to turn back round, wouldn't it? So if we have a light pulley, it stops us having to worry about turning forces in the pulley. We can, and if we have a frictionless pulley, there are no friction forces in the pulley, of course. So ask yourself the question: if this here is a mass of 3 and this here is a mass of 2, could this thing be in equilibrium? If you think about it, the only thing that would stop it being in equilibrium would be the friction on the pulley. If this is completely smooth, this has to be pulling down here more than it's pulling down here. The tension is the same all the way, so it has to be accelerating that way. Okay? If those masses are both the same, it could be in equilibrium, and in fact it would be unless somebody's deliberately pulling it down on one side as well. So if you just let two masses hang, then there would be, if they're both the same mass, the same same size mass, they would hang statically in equilibrium. If they were moving already, they'd keep going, moving at a constant velocity in equilibrium. If one's bigger than the other, then they're not balanced, so they will slip. In real life, they might not slip if one was bigger than the other, because there might be friction in the pulley. That would be the thing that would stop the thing moving. We're going to deal with frictionless pulleys, so there's always going to be a slip, there's always going to be an acceleration, because the forces aren't balanced. So this is the situation that we're dealing with. We're going back to this idea of if we've got connected particles, let's deal with each part of the system separately, except here we're not moving in the same direction. The acceleration is up on this side and down on this side. The magnitude is going to be the same. If this is moving with a speed of 2, I say speed, not velocity, deliberately. If this is moving with a speed of 2, this is moving with a speed of 2, not the same velocity, because this is going upwards, this is going downwards, and velocity includes direction as part of it. But the speed of the things is the same, and if the speed of the things is always the same, and the speed of this one is increasing, then the speed of this one is increasing in the same sort of way. So the acceleration's got the same magnitude, but this one's accelerating downwards, this one's accelerating upwards, okay? So what that means is we can use the same letter for the acceleration over here as over here, so we can put it in the equations in the same way. Now, I've deliberately picked a 2 and a 3, because there's a 2 and a 3 in the question, but in fact it's not a 2, it's a 2 times m, and it's a 3 times m. And there's a tension pulling up, tension there, tension there, tension there, always going to be the same. So this is 3m times g pulling downwards, this is 2m times g pulling downwards, and again that g is 9.8. That's the acceleration due to gravity. It's not a g for grams, it's not a unit. So there we go, there's our whole diagram. As with the examples in the last 2 videos, we are going to write the equations down before we do anything else. So we're going to, in the question it calls this Q and it calls this P. We're going to say at Q, we're going to consider vertical motion. I know there is only vertical motion going on, I know there are no forces horizontally, but it is worth getting in the habit of writing this down to say you are considering the vertical motion, because in so many situations there's some vertical motion, there's some horizontal motion, there's some motion in a different direction maybe. Tell us which direction you're looking in. So at Q, considering vertical motion, we are accelerating, so F equals ma is what we're applying. We must put this in to tell the examiner what you're doing. We're accelerating downwards. So 3mg take away T is the net force. Now, is the resultant force, I should say, shouldn't I? Let me just spell that out in case you haven't watched the previous videos. We take a piece of paper, or take your hand and cover it up. If we cover up the whole of the rest of the system, at Q, what have we got? We've got 2 forces, 3mg and T. 3mg take away T, that is our net force. That is equal to the mass, which is 3m, times the acceleration, which is a, and I'm going to call that equation number 1. Second equation, at P, considering the vertical forces, F equals ma, consider P on its own, cover up the rest of the system. T is pulling up, 2mg is pulling down. So tension minus 2mg, it's accelerating upwards, so the tension's positive, the 2mg is negative, equals mass, which is 2m, times acceleration, which is a. There's equation number 2. And now let's go back and say, well, what were they trying to find? So write down the equation of motion for P and the equation of motion for Q. Well, we've done that. We do that automatically. We never have to get asked to do that. As soon as we see the word pulley, we know we're going to draw this diagram or the one in the next example. And we're going to write down 2 equations, right? Find the acceleration, find the tension in the string. Let's look at these. We've got 2 equations, and they've got 2 unknowns in. We've got T and A. But this time, we've got a problem. We've got an M thrown in as well. So how are we going to deal with this? We need to find T, we need to find A. We should know that if we've got 2 simultaneous equations and 2 unknowns, that's fine, we can solve them. If we've got 2 simultaneous equations and 3 unknowns, we've got a bit of a problem. This is where, this is, I think, why the pulleys start to cause people problems, because that feels very uncomfortable. But actually, this is a common thing. When you've seen it a few times, it'll seem completely natural. There's a load of m's flying around. Let's not worry about it. I'm going to take this equation here, and I'm just going to rearrange it, just dead simply shifting that 2mg over the other side. And I'm going to relabel it. I'm going to call this one equation 2. And I'm going to say substitute from equation 2 into equation 1. What I get is 3mg from equation 1 minus, here's the tension, 2ma plus 2mg equals 3ma. So that is 3mg take away this 2mg, so that's just an mg, minus 2ma equals 3ma. So on this side, mg equals 5ma, taking this minus 2ma, shifting it over this side. Now look at this, look. Divide by m on this side, I get g. Divide by m on this side, I get 5a. So the m's vanish out of the equation, and I get a equals 1/5 of g. Okay? And remember, g is 9.8 acceleration due to gravity. So 1/5 of g meters per second per second. 1/5 times 9.8 meters per second. So all the m's cancel. So we had two equations, we had three unknowns. We just crack on, and everything was fine. Okay? At least it got us through part A. Then we look at part C. I'm going to take this and I'm going to substitute it back into equation 1 or into equation 2, and I'm going to try and find t. And this is the point where the pure mathematician and you should start really saying, hang on, we've really got a problem there. Because if I substitute this back in for A, I'm still going to get an equation with a t and an m in it. I get rid of the a, I found that one, and that g isn't really an unknown, is it? It's 9.8, we know what that one is. But I've still got an equation with an m and a t in it, so what do? Now, this is what at first seems like a really irritating convention in mechanics, but if you look at the answer, the part C was find the tension, and look, in the example they've given us, the tension they've said is 12 mg over 5. And then they've left it, they've said that's the tension. Nowhere in the question does it say find the tension in terms of m. I mean, okay, it's in terms of g, but again, we know what g is, so we could work that out. Why is it okay to leave it in terms of m? The answer is it just kind of is. We're sort of happy with leaving things in terms of m. I don't really know why that convention's grown up. After you've been using it a while, it seems to sort of make sense. I suppose it's because in a lot of situations, the m, the mass in mechanics questions, tends to sort of vanish, right? There's a lot of situations which you think would rely on mass but don't. So if you leave the mass in the formula, then sometimes it'll just pop out in the same way as it did here, right? You know, it didn't matter about the mass. We ended up being able to find the acceleration. The only thing that really mattered was that the ratio of these masses was 2 to 3. So often we leave it as m. This is 2 lots of something, this is 3 lots of something. It doesn't matter if it's 2 kilograms and 3 kilograms or 2 tons and 3 tons. If we know the ratio between them, we can work out the acceleration. So we're solving a slightly more general problem. But that just is the convention, that sometimes there's an m flying around, sometimes they expect you to leave the answer in terms of m, and they don't tell you that. You just have to know that. At first, I know that seems absolutely maddening. Trust me, do a few of the questions and you'll get used to it. Most people that have been through this mechanics course or a similar A-level mechanics course at some point have found themselves trying to do a question, trying to find the tension in the string T, and they're messing around with, you say, well, I've got it as 12 mg over 5, but I can't get rid of this m. What other equations know? What other information have I got in order to find m? And there isn't any other information. You just leave it at m. And eventually you give up, check the answers in the back of the textbook and see that you got there, and you got there half an hour ago, and it's really irritating. If that happens to you, don't panic about it. Loads of people have been there before you. You will get used to that convention and it will seem reasonable. At first, it seems completely unreasonable. Sorry about that, but it's the way it is. Now, let's have a look at the other questions they can ask us. Find the force exerted on the pulley by the string. That's not saying find the overall force on the pulley. That's just the force exerted on the pulley by the string. So the pulley, as we can see in this example here, has got a force pulling it upwards, and that force is provided by whatever it is that's fixed to the wall with or fixed to the ceiling with. But it's not asking about that, it's asking about by the string, and that is two tensions pulling downwards. So the force exerted on the pulley by the string is 2 lots of T, which is 2 lots of the answer to part B, okay? Now, find the distance moved by Q in the first 4 seconds. We know that it starts from rest because it tells us that up here somewhere the system is released from rest. We know that it's moving for 4 seconds, and we've found the acceleration that it moves with. So if we write down our information, U, V, A, S, and T, U we know is 0. A we know because we've found it. T is 4 seconds because that's what they told us. S is the thing we're trying to find. I've got one sorry, I've got 1, 2, 3 bits of information. I'm asked to find a fourth one. I can ignore the fifth. I'm using my Suvat equations, okay? So I would say that part E, in the way I think about it, that's not really a Pulley problem anymore. That's a Suvat problem. The Pulley problem always goes the same way. Draw that diagram, write down these two equations, work with those two equations. If there's anything else, read the rest of the question, see what you can come up with from what it says, okay? State how you use the fact that the pulley is smooth in your calculation. Because the pulley is smooth, the tension gets to be the same all the way through, okay? One thing I haven't mentioned here is an example of where the pulley questions stop and it turns into something else, but it's worth mentioning because they do this quite a bit. Here's a pulley, here's a mass here, here's a mass here. Let's say it's the same as the last question, it's accelerating this way, so this is a heavier mass. What happens if I cut that string, or if this mass hits the floor, so here's the floor, goes down for a bit, and then this mass hits the floor, what's going to happen? Well, this string, if it gets cut, it's going to the tension in the string is going to disappear. If this mass hits the floor, the string is going to go slack. At the point when the string goes slack, this object here is moving because it starts from rest, it moves, and then I cut the string, or it starts from rest, it moves, then this one hits the floor. This object is moving, and it's moving upwards. If the tension's gone, all that's happening now is its weight is pulling it downwards. So what have we got happening? We've got just an object that starts at the point when when this one hits the ground. This mass here is moving upwards with an initial velocity. Gravity's pulling it downwards with an acceleration of g. And then they can ask us questions like, what's the highest height that it reaches, in which case we'd be putting in v equals 0, or they could say, how long does it take until it reaches the height of the pulley? So, it might tell us the displacement, and we'd have to work out how long that would take, or they give us one more piece of information. They can ask us to find we know 2, they give us a third, we'd have to find a fourth. In other words, they can ask us a Suvat equation in that sort of way, okay? All right, at the risk of making this video a bit long, I'm going to crack straight into example 14 because I've said a lot of the funny little details here. So example 14, I can just do this is page 174, example 14, and it works like this. I can do just the other example of the two pulley equations. So if I've got this situation, I've got a mass hanging on a string, there's a weight pulling it down, there's a tension in the string pulling it up. That tension also pulls on the pulley and pulls down, and it's the same all the way through, okay? If it's then a horizontal table and there's an object sitting on the table attached to the string, well, the string is taut and the pulley's smooth, so there's a tension all the way through the string, and it's the same all the way. That tension pulls on this object here, and it pulls on the pulley that way, okay? This object on the table has a mass, so it has a weight pulling it downwards, and it has a reaction acting upwards. If it's a smooth table, there's nothing pulling it backwards. If it's not a smooth table, there might be a friction force pulling backwards, okay? I'll do the same I've done before, and I'll use the same numbers from the question. So in example 14, this is 0.8 times g. This is 0.4 times g. I can't say enough times these g's are g for gravity, 9.8, not g for not g for grams. We're calling that one r. 0.08 g is the friction force that's pulling it backwards. This acceleration here has the same magnitude as this acceleration here. They're not the same acceleration because acceleration is a vector quantity and they're going in different directions, but they're the same magnitude, so we can have the same letter, the same size acceleration, okay? So in this case, what do we do? Well, same as all the other connected particles questions. I'm going to label this one A and this one B. Same as all the other connected particles questions. I'm going to cover everything up, and I'm just going to consider B, vertically, its acceleration, so apply F equals ma. 0.8 g minus t, that's the overall resultant force, equals the mass, 0.8 in kilograms, times the acceleration, which is, mass, which is 0.8 kilograms, times the acceleration, which is a. Okay, that's equation number 1. I can consider A. Now I could consider the forces on A vertically, and then I would be resolving, and I'd get R equals 0.4 g, and I call it resolving because those forces are going to balance out. There is no vertical acceleration, but really I know there's nothing interesting going on vertically, so I'm going to consider A horizontally. I'm going to apply F equals ma, and I'm going to get, covering this lot up, tension's pulling it forward, 0.08 g is pulling it backwards. Tension minus 0.08 g, that is my resultant force, equals the mass times the acceleration. That's equation number 2. I'm going to take those two equations, I'm going to look at them, and that should sort me out, right? I've got a T and an A here, I've got a T and an A here. If I solve those two equations simultaneously, I should find the tension and the acceleration. Those will be the things that the question is asking me, and if it's asking me anything else, then I'm going away from pulleys, and I'm going to have to apply a bit of common sense and a bit of equation, of SUVAT kind of knowledge, or forces knowledge. When I look at it, part A, find the acceleration in the system. Great, that's what we're looking for. Part B, the time taken for B to reach the ground. I'm not sure what that means in terms of the pulleys. I'm going to have to go back and read the question. And when I do, I find that B starts 0.5 meters above the ground. We've worked out the acceleration. It tells us in the question it starts from rest. So we can use our SUVAT equations to work out the speed of B when it hits the ground. And then I'm going to leave you to look through part C, I think, but just quickly, what happens is when B hits the ground, A is going to keep moving along the table. When B hits the ground, A is moving at the same speed as B was moving at when it hit the ground, so I know how fast, where I can work out how fast A was moving. And then the tension force disappears, so all that's going to be left is that 0.08 g pulling A backwards, slowing it down. You can work out how long the displacement when A, the distance it takes A to stop, given the speed it's starting at, i.e. the speed when B hits the ground. Don't forget to account for that extra ½ meter that A moved before it hit the ground as well, if they're asking you to do that in the equation. It's all there in the blue box. But again, there's nothing new there. That is turning it into a SUVAT equation. Use a bit of common sense about when B hits the ground, the string goes slack, so what happens to the forces, then apply your SUVAT knowledge, okay? There is one tiny little corner of this that I haven't quite mentioned, and sometimes they ask us, so I'm going to deal with it now. If you've got a pulley on the corner of a table, and the question says, tell me about the force exerted by the pulley on the string. Well, again, this pulley would have a reaction from the table that stops it accelerating down in this direction, but it doesn't ask us about the resultant force on the pulley. It asks us for the force exerted on the pulley by the string. The string's pulling that way with a tension T, and it's pulling that way with the same tension T. So we can use a triangle of forces. We've got T pulling that way and T pulling that way. So the resultant is going to be at 45 degrees. 45 degrees because these two are the same size and they're at 90 degrees to each other. T pulling down and T pulling across. So by Pythagoras' theorem, you can work out the magnitude of this force here. Okay? So, well, let's just finish it off, I suppose. T squared plus T squared is 2T squared and square rooted. That's going to be the magnitude of the force. So the magnitude is 2T squared, square rooted, at 45 degrees to the vertical, also at 45 degrees to the horizontal, of course. There we go. That's the nasty stuff. That is chapter 10 finished. Good luck.